Okay, this is my second video for my Algebra 3 Prereq chapter number 3, in which we're going to concern ourselves with simplifying radical expressions where there are radicals in the denominator. And I'm just going to go ahead and start by saying that when you have expressions such as 1 over the square root of 3 where there's a radical in the denominator, or maybe even an expression with a loose radical over here, square root of 5 is in the denominator, and it's not even being multiplied by anything, what we want to do is we want to rid ourselves of those. So the first technique we're going to show here is called rationalizing the radical there, or rationalizing the denominator, okay? And what we do in order to remove a radical really is we do the inverse operation. What I want to do to get rid of a radical, what gets rid of it is squaring, okay, right? Or in this case, squaring, but taking it times itself in this case would produce a 3. Or, another way to look at this is we say the square root of 3 squared. If you took the square root of 3 times the square root of 3, it'd be the square root of 9, which is really just this 3 right here. Thing is with fractions, hypothetically, say I had a fraction here, the question would be, well, can I just square the top and the bottom of this fraction and get rid of things? Like let's say I had a radical there and I wanted to get rid of it. In this case, I don't, but square the top and the bottom, I get 4/9, and the question is, are these still equal? And the thing is with fractions, you can't just square the top and the bottom. What you really need to do is you need to take the top and the bottom times the same thing. So in this case, since I want to get rid of the square root of 3 in the basement, I'm going to say, well, what if I squared it or took it times itself? So I'm going to take the square root of 3 times the square root of 3 here, but the thing is I got to take the top and the bottom both times the square root of 3, because what you're really doing is multiplying by 1, which really means that you're keeping the same value here, that these two expressions will be the same. But our rationalization technique would be to multiply the top and the bottom of this expression that has a radical in the basement by the smallest radical factor that is going to give you a perfect square in the bottom. You notice that we choose the square root of 3 because the square root of 3 times the square root of 3 gives us a square root of a perfect square number, which is the square root of 9. Or you could say, well, the square root of 3 times the square root of 3 is just going to be 3, okay? And on the top here, I want you to notice also that 1 times the square root of 3, you would just end up with the square root of 3. So what we want to point out is that the square root of 3 over 3 is the same as the original expression, has the same value, but it doesn't have a radical in the basement. So let's take a look at these two expressions here, and I want to kind of point out some tricks of the trade. But starting with this 5 over root 3, this is very similar. Again, what I want to do is I want to multiply the top and the bottom times the smallest radical factor that's going to give me a perfect square number on the bottom. So when I say, well, what could I take 3 times? It's going to give me a perfect square number. Well, again, I can think of maybe 3 because the square root of 3 times the square root of 3 is the square root of 9, which really is just going to give me a 3. And as far as the top goes, well, we have to multiply by the same value here. So we end up with 5 root 3 on the top and just a natural 3 on the bottom. Now, you did hear me say that what we really want to do is multiply by the smallest radical factor on top and bottom that is going to give us a perfect square number in the denominator here inside this radicand. So when you think of 12, the thing is, I could take the top and the bottom times the square root of 12 or the square root of 12. And you know what? That's going to get rid of the radical in the basement. You'd have 6 root 12 over 12. And I'm going to come back to that there because that's not simplified, you guys. It's not. But if we were to say, well, what radical factor could I have multiplied by? Smallest radical factor I could multiply by to turn 12 into a perfect square number. The thing that comes in my mind is 3. I could say, well, 3 times 12 is 36. So I'd end up with this. I get 6 root 3 over the square root of 36, which the square root of 36, to my memory here is 6. So we get 6 root 3 over 6. And those 6's will cancel, and I get left with root 3. And this would be our simplified expression here, a rationalized expression. You could even write this as the square root of 3 over 1 and point out that the bottom is just a natural 1 now. So let's go back to this really quickly. Is this the same as what I have here? Well, it is, but the thing is you still have to simplify this. For instance, the 6 and the 12 here, this would become a 1, this would become a 2, and now I'm dealing with the square root of 12 over 2. And this is still not fun because now I got to say, well, the square root of 12 is the square root of 4 times 3 over 2, and the square root of 4 is 2. So now I've got 2 root 3 over 2, and then I got to cancel out the 2's, and I get left with this root 3 that we had here. Okay. So the idea is to multiply by the smallest radical factor that's going to give you a perfect square number in the bottom. But that's how we rationalize expressions. Okay. So now let's take a look at this example on the right here. You'll notice that I have written, it says radical expressions that involve a sum and a difference, okay? This would be things like square root of a plus the square root of b, or square root of a minus the square root of b. You notice we have a sum or a difference. The same two terms, if these are the same, square root of a plus square root of b, square root of a minus square root of b, these are referred to as being conjugates. In math, we say that any expression a plus b is the conjugate of any expression a minus b. And the nice thing about multiplying a plus b times a minus b, I'm just going to show everybody here, is this. When you distribute this, when you FOIL, you get a squared minus ab plus AB. So those factors are going to cancel out here. And then you would get minus B squared. So you really get A squared minus B squared, which in a radical sense, this is a difference of two squares. In a radical sense, if you were to do this with radicals, again, like take these and multiply them, the square root of A times the square root of A is just going to give me the square root of A squared, which is just going to come out to be A. In this case, I get, minus the square root of A times the square root of B. And then we get plus the square root of B times square root of A, which is still the same as square root of A times square root of B, and these terms cancel out. And then again, we still have a minus here. Square root of B times the negative square root of B is negative square root of B squared. So what you end up with really is just the square root of A squared, which is A, minus the square root of B squared, which is B. And you get this right here, where you'll notice that there are no radicals left in here. So what I'm going to tell you is you can always recognize when you're going to have to multiply the top and the bottom by the conjugate when you have a sum of two things, and maybe even one of them, it doesn't have to be both, involves a radical. So to simplify this expression here, what we're going to do is we're going to take the top and the bottom of this times the conjugate of the denominator here, which in this case, the conjugate of 4 plus the square root of 5 is going to be 4 minus the square root of 5. So let's take a look at this. We have 4 minus the square root of 5 on top and bottom. Now, with respect to the bottom, when you FOIL this out, what I want you to recognize is that you're going to end up with a difference of squares. So we'd say if this is like our A term, and this is like our B term here, we have A, B, A, B. When you talk about what you end up with over here, you're going to end up with A squared minus B squared. So in this case, we get 4 times 4 is 16. I don't need to take 4 times the negative root 5 or the root 5 times a positive 4, because those are going to cancel out. So we get our A squared minus now our B squared, and our B is like the square root of 5. So the square root of 5 squared, what do you get? Well, you get 5, okay? So in this case, we get 16 minus 5, and already I can tell you we've eliminated the radical from the basement, the denominator. So when I look at the top here, what is it that I have left to do? Well, we multiply straight across, and I can say, well, then I get 8 times 4, which is 32, and we say 8 times root 5 is going to be 8 root 5. Okay, you just get this here. And you know what? It is appropriate in certain instances. I mean, we could leave it this way. This has been rationalized. We no longer have a radical in the basement, but sometimes you'll have teachers that say, well, you know what, since you have a one-term divisor, a monomial divisor, what we're going to want to do is we're going to want to split that up. We say 8 root 5 over 11. These are both equivalent. I'm saying that I'm good with this right here, but that is how you rationalize the denominator.